recall. Okay, where do we stop? All right, let's just remember. This is the quiz. What is the definition of exterior measure?
The info.
Yeah,
No,
all together.
the inf over all coverings by almost disjoint.
It's kind of like, yeah.
Whatever you want.
Right. There are a bunch of equivalent definitions. Our definition, it will be countable covers of closed cubes.
And they don't need to be almost disjoint, right?
And they don't need to be also just arbitrary countable covers. The infimum of the sum of their sizes, and the whole point of using closed cubes is very clear what we mean by their sizes. So this is a set of RD. Okay, we proved a bunch of things about this. I'm not going to recall all of them, but what does it mean to be measurable? So this was definition of exterior measure. This is exterior measure. Definition E is measurable.
So you can find an open set containing E.
There's this
The different set having small measure.
containing E. I'm trying to catch up with you guys. Such that, if for every epsilon there exists an open set such that the exterior measure O take by E.
Yes.
Okay, good. Very good.
Do you have general advice of how to get at this different set? It seems like it's hard to access by the facts we have.
This different set?
Yeah. In general, yeah.
So that is actually one of the topics to discuss today.
Okay.
So basically, every measurable set differs from an open set by a set of measure 0.
Yeah.
These G delta and F sigma
Right.
sets. That's on the topic for today.
Yeah, but suppose you had like a set of finite measures.
Okay.
That's your homework, right?
Yeah.
That we save for office hours.
Okay.
Yeah, we can talk about it. I'm happy to talk about it. Okay, we were writing M is the set of measurable sets. Measurable sets. And what we proved is that M is a sigma algebra, i.e. closed under countable unions and complements, which then implies countable intersections and implies the empty set. The whole thing is in there. Okay, so countable unions and complements makes a sigma algebra. What about the Borel sigma algebra? We discussed this last time, didn't we? Yeah,
A little bit.
Borel sigma algebra is
Sigma algebra generated by open sets.
generated by open. The sigma algebra generated by open sets. And what's the difference between Borel and Lebesgue?
Differ by measure 0. So.
Right. Is Borel plus all sets contained in sets of measure 0, which then themselves have measure 0. Lebesgue plus measure 0 sets. There is a homework. I think I spared you of it, but there's a nice problem that you should think about if you have it, that proves explicitly that there are more things, that this really is what's going on, that there really are more things here that aren't just generated by opens.
Oh.
Okay. And that's as far as we got, right? And we were proving the main theorem of the whole point of this was if you have a disjoint countable union, then the sum of the measures should be the measure. And that's not true in general because of Vitali sets, but it is true for measurable sets. Okay, so that was our theorem that we will now prove. Theorem, if Ej are all in M, thus measurable, pairwise disjoint, and we set E to be their disjoint union, E is measurable because it's a sigma algebra, because the set of measurable things is a sigma algebra, then, which means you can measure E, and its measure is indeed the sum, as J goes from 1 to infinity, of the measures of the Ej. All right, let's prove this. Can't see from there, right?
Yeah.
Oh, okay. All right, so it's analysis. Equal signs only come with a greater than or equal and a less than or equal. Less than or equal sign is
Easy. Countable sub-additive.
countable subadditivity, which we proved already for exterior measures, so it's certainly true for. So this is done, and we need this direction.
Slide it a little bit.
Yes, thank you. Here's the theorem we're trying to prove. Okay. By now, this is hopefully familiar. What do we want to do? So here's our.
We take a little bit bigger sets, cover them.
Yes.
Take like some like really small open sets.
Right. We want to find open sets inside here. We want some distance between them so that we can apply what we proved last time about. Well, we proved a bunch of things, but right. We want a lower bound for why this sum can't be smaller than that measure. So let's look at E complement. EJ complement is each measurable because the E's are measurable. And if it's measurable, that means there exists an OJ which covers EJ complement and is open. We're going to do this. We're going to do this in two steps. The first step is to assume each of the EJs is bounded. Then we'll remove that assumption. So first assume the EJs are bounded. So we look at the complement. That's still a measurable set. There's some open set that contains the complement with, by the definition of measurable,
So outer measure of the difference is small.
yes. The outer measure, which now both of these are measurable, so I can just write measure of the, I won't put the star if I don't have to, of the difference is smaller than epsilon, but I'm going to want to add these things up, so I'll put epsilon over 2 with a j. Okay, so we have these OJs sitting inside EJ because they contain EJ complement. But this measure is also the measure of, so let FJ be OJ complement. These sets are closed because OJ was open. So FJ is OJ complement. Sitting inside this EJ is an FJ. Okay? And what is the measure of OJ take away EJ complement? That's this little tube. It's also the measure of
EJ minus OJ.
EJ, exactly. EJ take away FJ.
So we're really just like approximating from within like closed sets, right?
There you go. Okay? What's the goal of this? Well, we know that if sets are closed and bounded, as the FJs are since they're contained inside EJs, FJs are contained inside EJs. Since OJ contains EJ complement, the FJ is sitting inside, each FJ sits inside its EJ, and they're all bounded, and these are all closed, so they're compact. So each FJ does not intersect FK, and they're compact. So they have a positive distance apart. The distance from FJ to FK is positive. And what we proved last time is the exterior measure of a sum of two things with distance is the sum of the exterior measures. And these things are measurable, so I can just say the measure of a finite disjoint union of them is equal to the sum of the measures. Okay? We also have that this disjoint union is contained inside E, the total union. So by monotonicity, which way is it going to go? This is going to get bigger. If I throw in more stuff, it's only going to get bigger. On the other hand, so this is the sum as j goes from 1 to n. On the other hand, what we also have is that the measure of Ej, so Ej is Ej take away Fj plus Fj. Let me write it here. The measure of Ej, well, I don't know that it's equal to, but it's certainly at most the measure of Ej take away Fj plus the measure of Fj. So the measure of Fj is at least the measure of Ej minus this error. So each Fj is at least the measure of Ej minus the measure of this error. The measure of this error is at most epsilon over j, epsilon over 2 to the j. Epsilon over 2 to the j. So I'm just using finite subadditivity. I'm running this a little fast because I think we're getting familiar with this type of argument. And now we're done. What have we shown? That the measure of E is at least the sum, as j goes from 1 to n, the measure of the EJs minus a total of epsilon. And that's true for any n, send n to infinity. That's true for any epsilon, send epsilon to 0. N to infinity, epsilon to 0. And we get the lower bound in the other direction. Okay? Any questions on that? We're not done. We assumed that the EJs were bounded. Let me pause a second since people are still writing. How do we get from there to arbitrary EJs? For arbitrary EJs, so let's define a system that chops things off. So let's call S1 the closed ball of radius 1 about the origin. And then each, that's of course measurable. And from then on, each SK will be the closed ball of radius K about the origin. Take away the closed ball of radius K minus 1 about the origin. So this is closed, take away closed, so it's neither. Closed on one side, open on the other side, doesn't matter, it's measurable, that's all that matters. And of course, E, so the E, each EJ, let's put it this way, each EJ, so these are all disjoint. Thank you. These guys are all disjoint. Each EJ is the disjoint union, as K goes from 1 to infinity, of EJ intersect SJ, SK. These are all bounded and measurable. And E is the doubly countable, which is still countable, disjoint union of EJ-SK pairs. So I'm going to apply the previous theorem twice. I'm going to apply it once on E, which is a countable union of disjoint things that are each of which is bounded. And that gets me that E is the sum of all of these. But each of these is also a countable union of a bunch of bounded measurable things. So each of the EJs is a sum of all of these. So you group the sum of these into the sum of the EJs and you're done. Do I need to write that out or it's clear? So use bounded case and you're done. Any questions?
So are there there are the same EJs in the equations?
One more time.
There are there are two EJs here.
Well, this is a set. EJ intersect SK. So whatever EJ is,
Oh, yeah.
EJ might be unbounded.
Oh.
It shouldn't be drawn on this thing. It's okay. I'll put it right back where it was. No one will notice. The EJs might be unbounded, but I intersect them with these SK.
It's bounded.
Yeah. So this is EJ intersect S1, EJ intersect S2, and so on. These are all measurable, pairwise disjoint.
So SK is bounded.
Each SK is bounded by definition.
Yeah.
So I'm just creating this another.
So it's like an annulus.
Yeah, I'm just chopping things up into bounded pieces and applying it on each bounded piece. Okay. Yes.
Each EJ intersection SK is also bounded.
That's the whole point. Yes. EJ intersect SK is bounded because each SK is bounded.
The limits go to infinity also. Because we assume it's unbounded.
So the EJ, I don't know that the EJ is necessarily unbounded, but it certainly does recover, this intersection with SK does recover all of EJ. The union over all the SKs are a disjoint union of RD. I'm just chopped up space into compact things.
We use the first claim to prove this.
We're using the first claim, we're using the bounded case to prove the not necessarily bounded case. By breaking up the EJs into bounded pieces, applying the theorem for bounded decompositions to it. I never said up here that E was bounded
Yes.
in the original, just that the E.
Components are-
Yeah. So all we did is we subdivided E into pieces, each of which is bounded. Now we can apply the previous version of the theorem. Okay? Going once, going twice. Sold. All right. Let's prove some more things. Let me leave this theorem here just for now. Anyone still writing? Good. Okay, let's leave this here. Page 2. Okay, a couple more things I want to discuss with you before we move on to functions. All right, let's just get a little bit of notation, definition. If you have a bunch of nested sets and E is their union, what we'll write is that the EK converge up to E. Hopefully that definition is clear. The intuition for it is clear. Conversely, if the EI are nested the other way, they're decreasing, and E is their intersection, is something that's contained in all of them, we'll write the EK converges down to E.
Could you move the paper?
Yes. Thank you. Okay? And a corollary of what we just proved is that if the EJ are all measurable, then two things. The first thing is that if EK converge up to E, then their measures, by monotonicity, they have to be increasing, converge to the measure of E. And the second thing is if the EK are decreasing to E, then their measures converge to E.
Isn't there like a
With a little space for what's wrong with
you
this?
need at least one of them to be
Yeah,
finite,
I guess the
right?
then needed to be over here. And some measure, some EK has finite measure. Then this is true. Why can this fail?
We can look at open intervals on the real line.
Yes, for 2, look at, for example, n to infinity in the real line. If this is En, the intersection of the ENs, they're certainly all nested and getting smaller. The intersection is the empty set, which has measure 0, but all of them have measure infinity. Okay, so as long as at least one of them is finite, you've killed this one stupid counterexample that you always have to keep in mind. Okay, let's prove this. So 1 is pretty easy. If the EKs are going up to E, what are we going to do?
Define a new set where E, or let's call it F, maybe K is EK minus 1.
Perfect. Let's start with E1. And then after that, FK is EK, take away EK minus 1. Okay, so we know that the E's are getting bigger. This is E1, E2, E3, and so on. So just chop up their difference into F2, F3, and so on. Then E is the disjoint countable union of the FKs. By the previous theorem, the measure of E is the limit as n goes to infinity of the finite chops.
That being the measure of that.
The measure of that, thank you.
And that telescopes, doesn't
That's part 2. So I'm proving part 1. If we're increasing up to E, so E is the union of all of these things. The point is when we stop at level n, what do all these measures add up to?
Yeah.
The measure of EK, of En.
So is that a sum or?
Thank you.
Oh, it should be a sum.
Oh yeah, it should be so.
I'm trying to say that the union, it's both. The limit as n goes to infinity of the measure of the disjoint union of the FKs as k goes from 1 to n, which is the limit as n goes to infinity of the measure of En. So far, so good? All right, I don't think I need this theorem here anymore. We know what it says. You can see. Okay, proof of part 2. Well, eventually one of them has finite mass. Let's just assume E1 has finite mass. Throw out the finitely many that you don't care about. Assume the measure of E1 is finite. So now we have E1 is the biggest one, and it contains E2, and it contains E3, and all the way down to E down at the center. So we'll do
So E1 minus E2 then.
Yeah, we'll do exactly the same thing. Let's let F, what do we want to call this? F1, I guess. F1 is E2, I guess E1 take away E2. So that's this little annulus. This is F1. And then F2 is E2 take away E3. And so on. So this is F2. Then E1 is the disjoint union of the F's
With E.
plus E. The F's will only telescope down to whatever this limiting intersection of all of them is.
But they always miss E.
They always miss E, because they're always throwing away whoever the next guy was. So I have to put E back in. This is a disjoint union, so that tells us the measure of E1 is equal to the limit as n goes to infinity of the sum of the measures of the Fj as j goes from 1 to n plus the measure of E. That's just applying that previous theorem. Sorry, I'm in your way. I see it was useful when the table was over a little bit because then I could never have to worry about being in the way. Let me slide this up. Is that better? Now let's look at what this measure is. The measure of Fj, each one is the measure of E1 take away, the first one's measure of E1 take away E2, plus the measure of E2 minus the measure of E3, plus the measure of E3 minus the measure of E4, and so on. So this is the measure of E1 plus minus the measure of E2 plus the measure of E2 minus the measure of E3, all the way down to minus the measure of En. So everything telescopes except the first term and the last term. So what we've shown is that I'm keeping this side, the measure of E1 is equal to the limit, let me leave a little room, the limit as n goes to infinity of minus the measures of E1, of En, plus the measure of E1, of course that doesn't depend on n, so I can pull it out. And then what's left over is the measure of E.
What are the conditions for being able to say that the measure of a difference is the difference of the measures? Didn't we do that in that sum?
In this sum?
Yeah.
This is a finite sum.
But like we broke up measure of Fj as
Yes.
the difference of two measures.
Two measures with disjoint. So we're writing. Let's put it this way. You write Ej as disjoint union of Ej plus 1 and Fj.
Yes.
And now you apply the previous theorem for finite disjoint unions.
Gotcha.
So at the level of finite disjoint unions, everything's okay. Even countable disjoint unions, everything's okay. Here we're just doing finite disjoint unions. And it's only at this point that we're going to use that the measure of E1 is finite. The beauty is we can subtract it from both sides, which means this thing minus this limit is going to 0, which means the measures are going to the measure of E. Let me just put it here, which implies the limit of mu En is measure of E.
Should it be En plus 1? It doesn't. I guess it doesn't.
Yeah. Oh, Bob. Is that still something you guys know? You know what that means? Oh, Bob. Off by one bug. You didn't call it that. If you're programming and it's supposed to run from 1 to n, it's really from 0 to n, or 0 to n minus 1, or 1 to...
Sounds a lot nicer than what I called it.
Yeah, we called it an OBOB back in my day. All right, any questions? Okay, so if you have these telescoping sums coming, or not, if you have nested sums coming down, as long as you start with a finite amount, you're going to converge on the limiting measure. If you have something from the inside coming out, you're going to converge on the limiting measure, no matter what. Because, well, if any of them is infinite, then the whole thing's infinite. There's nothing to say. Okay. Good. Let's get to that theorem that we were talking about. So any measurable set, let me slide this up, theorem. What I want to say is measurable sets are well approximated from the outside by opens and from the inside by closeds. So let's make this precise. Well, let me write that just so the philosophy is down in your mind. Any E which is measurable is well approximated by opens and closeds. I.e., let's make this precise. So here's theorem 1. If you have a measurable set, for every epsilon, there exists an open set containing E such that the measure of the open set minus epsilon minus E is at most epsilon. That's the definition. That's not a theorem, that's a definition. Okay. So slightly less trivially, there exists a closed set contained inside E such that the difference of E take away F is also less than epsilon. Slightly less trivially, all right, now I need the measure of E. So not only can you do this with closed sets, you can do this with compact sets. If the measure of E is finite, even if E itself is unbounded, there exists a compact subset of E such that the measure of E, take away this compact, is less than epsilon. And the fourth thing, which may be useful, is, again, if the measure of E is finite, then there exists a collection of closed cubes, a finite collection of closed cubes, Q1 through Qn, and let's set F to be their union, not necessarily disjoint, that doesn't matter, with, well, I've only used finitely many, and I didn't say they were inside or outside, so let's use the set difference. The set difference is at most epsilon. Does everybody know what set difference is? If I have E here and I have F here, well, that's a bad picture because I want them to actually overlap on most. In this application, I want them to overlap on most of space. But the set difference is this and this. In other words, this is equal to E take away F, disjoint union F take away E. Somebody who's in one but not the other. Okay, let's prove this theorem. Good. Okay, proof. As we said, 1 is the definition. 2,
Is it just the definition for the complement?
yes. Apply the definition to the complement, which is measurable. 3. Now what?
We could start with a closed set
Yeah.
inside.
There exists a closed F contained in E such that the measure of E take away F is at most, let's call it epsilon over 2. So here's E, not necessarily bounded, bless you. We found an F inside of it. We're assuming E has finite measure. We found an F inside of it. So here's, maybe this is a bad picture. E is here, F is inside of it, that's closed.
Yeah, but it might not be bounded.
But it might not be bounded.
We just like chop off part of it.
Let's chop off parts of it. So F is equal to the disjoint union of F intersect SJs,
Yeah, those are the balls.
where the SJs are these closed. Doesn't that? Yeah, and those are the ball things.
Right, so then we can find the measure of F as the sum of those measures.
The measure of F, right? The measure of F is the sum of the measures of these bits as j goes from 1 to infinity.
Do we want to do that, or do we want to do something? Do we want to use like the limit of that union because it's increasing, right?
It's increasing,
Yeah.
but why does this converge? Because the measure of F is at most the measure of E, and the measure of E is finite. So this sum converges.
So its terms go to 0.
Not just its terms, it has its tails.
Go to 0.
Its tails, which implies there exists an n with the sum of the measures from, should we not make obobs now? N plus 1 to infinity?
Can we move the paper up just a little
Yes, Cleo. Can you see that? F intersect Sj being at most epsilon over 2.
bit? So what, we just add those two things together, and we get an epsilon on the right-hand side.
So we add those two things together. We get
It's the left-hand side of the right thing.
Okay? Does everybody see that? So,
What What do you need bk minus 1, 0 only and not solution?
One more time?
The bk minus 1, the definition of SK.
Yes?
We need union of closed sets.
Yes. But now look at what happens. So let Fn be the disjoint union as j goes from 1 to n of F intersect Sj. That is just F intersect the ball of radius n closed. So these guys weren't individually closed, but this is now the intersection of two closed sets. So we've taken this big ball of radius n, intersected it with F, and we have this Fn, which is closed and bounded and hence compact. And then the rest is exactly what we said. This difference is at most epsilon over 2, and the difference when we drop the tail is again at most epsilon over 2. Do I need to write it? Or should I write it? Yes, okay. So the measure of E take away, what are we trying to prove? Here's our compact set Fn is at most the measure of E minus the measure of Fn. The measure of Fn is, I can make it even smaller at the cost of epsilon by sticking in, so this is the measure of E, take away, I'll put everything else back in, so that's the measure of F, minus epsilon over 2, I guess plus epsilon over 2 since I have a minus sign here. And this is also at most epsilon over 2. Okay. How about cubes? So any questions on, you can find a compact set inside?
So why would we think to like split it up by annuli rather than just split it up by balls? I guess because we want the disjoint union? Is that why?
Yeah.
Okay.
Could you directly argue that you can get a ball big enough that it contains most of the measure of F?
Yes.
Okay.
I find it easier to think about it in terms of, I don't know, it's 1/2 dozen, 6 1/2 dozen. What is it? Yes, that's it, 6 1/2 dozen. Yeah, you could have just as well said, this is the limit as n goes to infinity of the intersection with the closed n ball about the origin. And so that limit must eventually get within epsilon over 2 of this thing. So you don't have to think about tails. I don't know why I like convergence. Okay? Now I'm going to slide this down so we can look at the last thing that we're trying to prove. Let's do this. So here's a proof of 4. Let's slide it back up. Okay, so proof of 4. We want to find these closed cubes, a finite number of closed cubes whose set difference is not too big. So step 1, from the definition of exterior measure, which is also a measure on measurable sets, so there does exist a collection of, an arbitrary collection of closed cubes. Let's see, closed cubes, which covers E, and the amount by which it overcovers, and the actual measure of E is at least the total sum minus epsilon over 2. So it overcovers, but not by too much. That's just because it's a limit. The definition. Okay. We want to be able to throw away lots of them, so we'll use exactly the same. We want to throw away all but finitely many of them. So we use exactly the same argument as before. How do we do it? Yes?
So this infinite sum converges, so take a capital N such
Yes.
that the tail has sum
Yes.
at most.
This is where we're again going to use that the measure of E is finite, which implies, so the previous proof was a warm-up for this proof. Now it's mutatis mutandi, right? You just change the words, everything else the same. So there exists an n such that, that's why we could have done the previous one just as well using balls, but if we do it as tails, then we prove in the same way both theorems. So that the sum from n plus 1 to infinity of the size of these qj is epsilon over 2. And now let's look at the measure of the set difference. So that is at most, well, it's equal to, in fact, the measure of E take away F. What is F? Of course, F is our union as Q goes from 1 to capital N. It's what we were calling Fn previously. Plus F take away E, plus the measure of F take away E. So the measure of F take away E, I mean, we're basically done here. How do I want to say this? The measure of F take away E, I will bound by the measure. So the measure of E take away F is already here. What am I trying to say? It's clear, right? I'm trying to do this too fast. E is contained in the QJs. So E take away F is contained inside this tail. Because I've taken away the first n guys, and all of them cover E. So all of them cover E, but you take away the first n ones, that's the union of the remainder. That's this is at most this, because of containment. Plus F take away E. Well, I don't know what's in F take away E, but I know that if I increase F to all of them, that only increases the sum. So this is the union over all of the Qj, take away E. This is at most epsilon over 2 by this previous construction. This is at most epsilon over 2 by this construction. And we're done. Question?
Can we make this disjoint cubes as well?
Can we make them disjoint cubes? Well, yes, because we proved another theorem that measurable sets are almost disjoint unions of closed cubes. But yeah, that's not what we were going for. But yes, by the same argument, if you wanted to make them disjoint, you could. Okay, any questions? So the moral of that story is measurable sets are approximated from above by open sets, that's just a definition. They're approximated from below by closed sets, that's again basically the definition. Moreover, you can make it compact as long as you have finite measure. And if you want cubes, you can cover with cubes, and then the set difference will be very small.
So this move to the set difference at
Yes.
the last step, we're using something, because what we had up there was a difference between the measure of E and the sum of these cube sizes. And what we have downstairs on the right is a measure of a set difference.
This.
Yeah. So
this measure is, let me put it this way, this measure is equal to this measure plus the measure of E. Because they're disjoint, and this contains E. So that's where I'm able to separate the two.
Yeah.
Does everybody see that?
What did you say was this?
Yeah. So the question is, how come I'm allowed to break this up into the measure of this sum minus the measure of E? And it's because the measure of this sum, well, this union, is equal to the union take away E plus E. And that's a disjoint sum.
Oh, right. Okay.
So that's where I'm going. That's where I'm using this equation.
Do we need the measure to be finite to do that too? Are we like subtracting something across somewhere?
They are all finite.
Yeah, they are.
It's true that I'm subtracting because I'm expressing this as a sum,
Yeah.
and then moving the sum to the other side. Yeah. Okay? Next. Very good. We're making good progress. What else do I want to tell you about? Are we up to... let's talk about G delta and F sigma sets. That's next. Okay. So some obvious, let's just record some obvious facts. You'll tell me why they're obvious facts. The measure of E translated by H, so this is, by E translated by H, I mean the set of all x plus H, where x is in E. This is all happening in Rn, or Rd, so H is a vector. Oh, I gave it away. Oh no, I didn't. This is just the definition of E plus H, is just translate. What is that equal to? The measure of E. Why?
Because we can translate.
Because you can translate cube by cube, okay? Or you can translate open set by open set. The measure of a dilation, which is just take every point and scale it by delta. Delta to the power d times the measure of E, because
Scale the cubes.
scale each cube. Each cube scales by the dimension. Okay? And what about the measure of minus E? That's minus the measure of E.
What is minus?
Minus E is you have a reflection across the origin in Rd. So these are things that are special to vector spaces. So this is the set of all, just as before, it's the set of, you do the operation pointwise. Okay? Good. And all of these things are measurable, I should say, before I put the word M in front of them. The letter M in front of them. Okay, so theorem, if you have a measurable set, then two things. That is equivalent to, oh, I need a definition. Ha ha ha. There exists, let me write it and then I'll tell you what these things mean. There exists a G delta containing E with G delta take away E having measure 0. And being measurable is also equivalent to there being an F sigma set contained in E with measure of E take away F sigma being 0. Where, it's a definition, where, definition, what's a G delta set?
Geöffnet Durchschnitt.
Yes. If your German is good, you need both German and French to understand these, unfortunately.
So it's an intersection of opens.
Right. A union of opens is always open, but the intersection of opens need not be. But a countable intersection of opens is what we mean by a G delta set. So it's not open, it's just a countable intersection of opens. And what is an F sigma set? A countable union of closed, and the French is
Fermé zoom.
fermé sum, yeah. Do we still have language exams?
No.
Closed. How do I write closed? K, F, F, J are closed. We don't have language exams anymore because we have Google Translate now. Okay, fine. I'm okay with that. I think I even voted for that. Okay. Right. So that's the theorem that we want to prove. So by G delta, I mean countable intersection of open sets. Not necessarily open at all, but still something very useful. And F delta is countable union of closed, not necessarily closed, but up to sets of measure 0, that's all that measurable sets are. Okay, so we have a bunch of things to prove. These proofs, again, are, kind of tedious. So let's prove one in the that way direction. Okay? So the first thing to observe is that any G delta set is measurable. Maybe I should just write it here. As are F sigma sets, they're measurable too. Hello, spider. I'm busy here. And then what do I want to say?
Just write it as a union of, or write G delta as a union of E in a measure zero set. Is that what you want?
I want to say G delta is a disjoint union of E, disjoint union, this set which has measure 0. So what?
Differences of measurable sets are measurable.
And differences of measurable sets. Okay, so E is given as, in other words, E, how can I, G delta contains E. Anyway, this is trivial. Here's E, G delta is a little bigger. So how can I write E in terms of, this set has measure 0 and hence it's measurable. G delta is measurable. I'm trying to prove that E is measurable, so I express E as G delta,
minus G delta minus.
right, G delta, what's my notation there? G delta complement, that'll get this. Take away G delta, take away E. I think that does it. Anyway, it's obvious. You express E as a measure 0 set which is measurable as some combination of two measurable things using things that preserve measurability. So E is measurable.
You don't want to complement that.
Yeah.
G delta, sorry. I want to take G delta and I want to take away this measure 0 set that recovers E. Yeah. And all of these, this is a set of measure 0 and hence measurable. This is measurable. This operation is preserved by the actions of complements and so on. All right, how about in the other direction? So that proved that if there is a G delta set that contains E with set difference having measure 0, then E is measurable. Now if E is measurable, then for every integer, I want to make this countable. So let's use integers. There exists an open set containing E with the measure of O(n) take away E at most 1 over n.
Their intersection.
Yeah, so then I'm going to set my G delta set to be the intersection of all these O(n)s. Let. Okay, then the measure, I think it's clear, but let's just finish the argument. The measure of S take away E, S is a G delta set. The measure of S take away E is bounded by the measure of any of these O(n)s take away E, since the O(n)s become smaller down to E, and each of these, well, it's not even that they become smaller, this is the intersection.
Yes, intersection.
So it's in each one, and I've taken away E. And that has size at most n, but this side had no n's in it. This goes to 0. The only thing that's bounded by a sequence that goes to 0, which has nothing to do with the sequence, is the number 0. Clear? Pretty easy. All right. Should I bother proving 2? No, it's the same. So proof of 2 is the same. In the interest of time, let's keep going. Any questions?
Do you mean the same proof, or you
Same.
use the proof of this? Or
Use the proof of this
statement
on the
this
complement.
and then complement.
Yeah. Take E complement.
Can you explain the first step why E is measurable because of G delta complement
Okay.
minus?
So this first proof is that 1 holds in that direction. So we're assuming that there exists a G delta which contains E with set difference having measure 0. So G delta is E disjoint union G delta take away E.
Yeah.
That's just G delta is E plus the set difference. G delta by construction is measurable. This thing has measure 0. And any set of measure 0 is measurable.
Yes.
So E is G delta take away this tube.
So there is no complement.
There's no complement.
Yeah.
That's crossed out.
Yeah.
I guess it's not crossed out very well.
That's why that confused me.
Yeah.
Because it's
Yeah, it's not complement. It's much simpler. That was me.
that sounds.
Okay. Other questions? So far, so good? All right.
Why do we have both ideas?
Why did we have both ideas?
Yeah, did the French and the Germans just like not like each other for some reason?
That's a good historical question, especially because the notation, yeah,
I can think of some reasons why they didn't like each other.
that's a great question. I'm going to write that down.
Are they
Why
the same
Both.
or complements of each other?
Yeah, they're complements.
But
The
is
complement of an
every-
F sigma is a G delta.
So certainly that. Do you also have the non-trivial fact that they're actually exactly the same, or no?
What do you mean they're actually exactly?
Is every F sigma set a G delta set?
No, it's every F sigma is the complement of a G delta. And they're all measurable, so they differ from one another by sets of measure 0.
Oh yeah.
So every F sigma differs from a G delta by a set of measure 0.
Huh.
But there's no reason for them to be exactly the same.
Okay, that's what I was wondering.
Yeah. Why both G delta and F sigma? This is a good question. I like this. You see, I like human mathematics, not Bourbaki style lemma proof. Just know this stuff. Like, why? Who cares? Why do people do this? So that's a good question. This is just very standard terminology at this point, but you don't really need both since they're obvious. Obviously, you can work with one or the other. Sometimes it's useful. You see, closed sets, open sets are great because they're open sets. Closed sets are good because they're close to compact sets. So, yeah, you can cut them up into compact sets. And compact sets are obviously very useful. So maybe there's a good reason to have both, but it's kind of funny. I'm curious where this notation was used for the first time, why they used German for one and French for the other. I don't know the answer to that, but I'd like to. Okay, let's get to functions. We have a little bit of time to talk about functions. So we're going to start to build up the theory of integration, but first we have to talk about what it means for a function to be measurable. So let's work that up a little bit slowly. So first functions that we should think about. First, measurable functions. Measurable functions are the characteristic functions. Characteristic functions. So f of x is the characteristic function of some set E which is measurable, which takes the value 1 for x in E, and the value 0 if x is not an E, where E is measurable. Okay? Doesn't have to be, we don't care about continuity anymore. Oh, we do, but not yet. Okay? Our first measurable function is this. More generally, so here's the general definition. Bless you. F, let's say from RD to R, although, I mean, obviously this definition will generalize. And it's actually convenient to sometimes allow plus or minus infinity. So this will be the extended real numbers. And I'll say a function takes finite values if it doesn't land in plus or minus infinity. Is measurable if and only if, let's put it this way, for every real number, the set of f lying below that real number, i.e., this is the set of x in, well, it doesn't even have to be defined on all of RD. Maybe it's only defined on some subset of RD. The set of x in the subset where f is defined, whatever its domain is, such that f of x is less than a. Another way, again, of saying this is f inverse of, well, I have an a upper bound, I have a minus infinity lower bound, but maybe it actually hits minus infinity, so let's include that as a possibility. So this is a subset of E. We can ask if this is measurable. If for every A, this set is measurable. This set is in. So a function is measurable if the pre-image of any set like this is measurable.
So how does adjoining plus or minus infinity to R affect the topology on R? Does that mean that closed interval minus infinity to some open interval is open?
Yeah, so this you can put the isolated, the discrete topology on these two endpoints and keep the rest of the topology
Right,
here.
you just add on.
Just add on to it. So for example, we will eventually want to think of measures as functions. Or here, I mean, we've basically done it here. So it's possible for, no. What am I trying to say? Measures can take infinite values. So it makes sense to allow functions to sometimes take infinite values. Usually we'll want them, especially if we are integrating, we'll want that to happen on sets of measure 0 at worst. So we really don't, I mean, most of our theorems will be about regular kinds of functions.
I want to argue with you a little bit
Please.
on the point. I think we should put the topology of closed interval 0, 1 on R union minus infinity, infinity, in the sense that R is in nice homeomorphic bijection with open interval 0, 1, and then you can add infinity at the endpoints.
Sure, that's another way of. We're not really going to do any serious topology with this. You're saying you can map open 0, 1 to open minus infinity, infinity, and then stick 2 more points at the end of it.
Yeah.
The same way as closed 0, 1 has that topology.
Yeah.
So it's the relative topology to restricting to 0, 1 closed. In other words, here's how we'll settle this. Is this set open for you?
Yeah.
Yeah, for me too. Good.
Okay.
Can I just ask in terms of, if f is continuous, right,
Yes?
then the question is, that if that's an open set, it gets mapped to an open set, and so it's trivially measurable,
Yes.
right? I want to be able to say that.
Yes.
'Cause otherwise,
We
if you
will say
can't-
that in a minute.
If you can't say that, then it's like things get kind of
Yes.
weird.
The definition of continuity is that the inverse image of open sets is open.
Excuse me.
Yes.
Could you please give some motivation for why this definition?
Okay, that's what we're about to do. We're about to prove a bunch of lemmas. That motivate the definition.
Are we talking measurable about the x? It's not about f. It's about x. Right?
That's right. So this is an abusive notation. It's a shorthand for the set of X. This is a subset of RD. I want to know, is this set measurable, but I will abuse notation and write this most of the time. Or if I want to be, I don't know, really reverse or something, I'll write minus infinity with a closed bracket. Okay. So let's get to why. Okay, so what the definition that we really want is that the inverse image of open sets is measurable. That's one equivalent definition to this one. This is 100. I don't think I'll go over all of them, but I will go over some of them. So so here are a couple of lemmata. So here's a lemma. This is our definition. Lemma. So a function f, let me immediately remove this issue of plus minus infinity, which is finite valued, is measurable if and only if, all right, let's do it one step at a time, for every open set. The inverse image of that open set is measurable. And the same thing will prove that this is true if and only if for every closed set, the inverse image of the closed set is measurable.
Why do we need f to be finite value? Didn't we call those weird intervals up above open?
We did. What I don't want is I don't want to. You'll see in a second. You'll see in a second. I think, or maybe I'm just being lazy, and I don't want to discuss the topology on. I want to be. We can put it, and we've already put the topology, but I want to maybe be vague about this. Let's just give a quick sketch of this. The point is, I've defined this in terms of this inequality, but I could just as well have defined. So note that what I really want to say is that the set of f where f is at most a with an equal sign is the intersection, the countable intersection of f being at most a with a strict inequality plus 1 over k. So if all of these sets are measurable, then their countable intersection is measurable. So preimages of closed sets are just as good for a definition of measurability as preimages of open sets, of closed intervals. And for the same reason, complements are just as good, because the complement to this and the set where f is greater than or equal to a, complement is, of course, the set where f is less than a. So it's things like this that I want to not deal with the value infinity. Right. So, yeah, and this idea. So that's, I mean, that's the sketch. Once you get intervals, you know that every open set is a union of intervals, countable union of intervals. So everything follows. I just want to point out what I would need to also assume here is if f inverse of plus or minus infinity individually is measurable. So I could replace finite valued with if its value at those two endpoints is measurable. Then everything is equivalent. Okay. And let's prove an important lemma. If f is continuous on Rd, then it's measurable. The proof is immediate. Proof. Now, so not everyone has seen why continuity means that the inverse image of open sets is open, or has everyone? Okay, everyone's seen it. Okay, just checking. Continuity is equivalent to, or in fact should be defined as, since once you don't have metric spaces, if you just have topological spaces, you can still define continuity this way. The inverse image of open is open. I mean, this is not the same open. Yes?
Isn't f inverse of plus infinity equal to the countable intersection of f inverse of a comma plus infinity close?
You mean back here?
Yeah.
The point is, I'm not. I was trying to avoid putting an actual topology on this thing, so that's why I restricted to open sets in R, and then I don't want to talk about what it means to have. I mean, yes. The short answer to your question is yes. You could just take A to be negative n or something,
Yeah.
and take the intersection of all those.
Yeah.
Yeah, that's
But
another.
that's what I think points you don't need that hypothesis, right?
So it's not an extra.
Well, what that would look like in as a subset of R is that would look like this set.
Oh yeah, that's right. Okay. So then we're still asking the same.
We're still asking the same question because we're not saying. We're still asking about the finite values of f without ever discussing the possibility that f takes on infinite values, positive or negative. So this is making those positive, negative, infinite values explicit. Again, what I should perhaps just have done is put the topology there, and then I could say R union plus or minus infinity.
It's okay.
Right, so if the pre-image of an open set is open, well, open sets are measurable. And so continuous functions are measurable. Open sets are measurable. All right, here's a very important lemma. So if f is measurable, I have to get this in the right order, and finite valued. Let's keep things simple. And finite valued. And so f is measurable, f from where to where? F is from Rd to R. And I'm going to compose it with phi. And I have a function phi, which is from R to R. And it's continuous. These are my assumptions. Then f composed with phi, so this again is from Rd to R, is measurable. There's an exercise that if we put this in the other order, or if I change which one's measurable and which one's continuous, it's no longer true. Okay? Note. Well, I can't just change them in the other order because then if right, if f is continuous and phi is measurable, then f composed with phi. So I go from R to R and then
Wait.
What is your
I have to change which one's which. F from R to R is measurable.
Just keep the same order.
I could just keep the same order. I want to change the order to make the point, but let's make this one then I'll keep the same conditions. Measurable. So if f is from R to R is measurable and phi is continuous. So if you take a measurable function and then compose it with a continuous function, you get a measurable function. If you take a continuous function, you compose it with a measurable function. Seems like what's the deal? What's the big difference? Not necessarily measurable. Not necessarily measurable.
So which one is now continuous?
So you can't compose two measurable functions and guarantee measurable functions.
Right.
You can compose a measurable function with then a continuous function.
Right.
Continuous functions don't screw things up against measurable functions.
On either side?
No.
Sorry.
If you first do a continuous function, then you do a measurable function, you might get a not measurable function.
Yes.
And there are Cantor set examples. You can basically get something that has sets of measure. You can do Cantor set constructions. That's what this exercise is.
Something that can go wrong on sets of measure 0.
Right. Okay. All right. But let's prove the lemma. So this is just a warning. This is not. It seems like yes, of course. Let's just keep moving. No. There's something to do here. So let's prove the lemma. So what is the point is that the pre-image of f is going to be a measurable set, and phi is continuous. So how do I want to say this? Phi.
Yeah, the image switches their order, right? And that's where.
Right. So we have to be careful about what we mean by this. This means do f first, and then do phi. Right. This is a function from Rd to Rd. Rd to R. Okay. So what I want to say is phi is continuous. What does that mean? The pre-image of minus infinity to a is open. And what does that mean? That means if I take phi composed with f inverse on minus infinity to a, well, that is equal to, did I give this open a name? That's f inverse on an open, which is measurable. Let's go through this again. Phi inverse of an interval, this is open, it's continuous, it takes open sets to open sets. F inverse on open sets, by definition, of f being measurable is measurable. So this, not concatenation, composition, thank you. So this composition, inverse of an interval, is measurable. That's what it means to be measurable. If we had it the other way around, we would say, what's the inverse image on a continuous function? What's the inverse image of a measurable set? No guarantee that that's measurable. Continuity doesn't tell you what happens to the pre-image of measurable sets. Okay, so that's what goes wrong in that case. Okay, do I have time for? Yeah, let's do just a little bit more, if we can. Here's a tiny lemma in a tiny space. If you have a sequence of measurable functions, then their sup is measurable. So if fn is measurable, then the sup of fn, just pointwise, is measurable.
By fn measurable, you mean every function?
Every function is measurable. Each function is measurable individually, and let's say converges pointwise to some function, then that function is measurable. Let's prove that. Well, if I look at the sup over fn being less than a, in other words, the set of x for which the sup of fn at that point x is less than a, that is the union of the fn's being at most a. If the sup is at most a, then all of them, then that's the x's where each of them is at most a, and you take their union. These are all measurable. The union of measurable sets is measurable. By that same token, let me use another page. So the same thing, gives that the that the inf, I'm getting to the limbs in a second, that the inf of fn is measurable if it exists, and the lim sup, which always exists, and lim inf are measurable.
Shouldn't that be the intersection on the first one?
Sorry. That's better. So I want the opposite. If the sup is bigger than a, I'm getting up to something, and what I'm getting up to is I'm going over a. Well, that happens if all of them go over a. Or you can do the intersection with less than sign.
Sup is bigger than a if at least one of them is bigger.
Exactly.
Okay.
Which is why it's the union.
Okay. Great.
Okay. Same thing tells you that the inf, if it exists, is measurable, and then the lim sup. Why is the lim sup and the lim inf measurable? The lim sup, well, that's the inf over all k of the sup over n greater than k of fn. And this is measurable, and this is measurable by the previous two things. All right. I was hoping to get to one more thing, but we're going to